Hi, in this video we will review our topics for our test 3. These are the topics that we will be covering in our test 3. One is on the single phase transformers, which covers the ideal representation and non-ideal representation of the single phase transformer, and then we will be covering three phase transformers also. To start with, we will review the single phase transformer, especially the ideal representation. In the case of a single-phase transformer ideal equivalent circuit, we consider that the transformer doesn't have any voltage drops, and transformer also doesn't have any leakage fluxes, and transformer doesn't have any losses. It indicates that the voltages on the primary side of the transformer and voltages on the secondary side of the transformer are related through the turns ratio of the transformer like this. Our V1 multiplied by N1 will be exactly equal to V2 multiplied by N2. And as we know that the transformer is a power invariant device, it is also to be noted that the power on the primary side, which is V1 multiplied by I1, will be exactly same as V2 multiplied by I2. This also gives us one more relationship that corresponds to the currents on the primary and currents on the secondary. From these two equations, we can clearly understand that the currents on the primary of the transformer and secondary of the transformer are related exactly opposite to that of this equation. I1 upon N1 is exactly equal to I2 upon N2. These are the three fundamental relations that we have in the case of a single phase ideal representation of the transformer. Now, if you wanted to have a simplified representation of this equivalent circuit, the load impedance that we have here can be brought on to the primary side by properly adjusting the value of that impedance. We want to simplify this particular equivalent circuit and represent the total load impedance onto the primary side of the transformer itself. Then this load impedance can be referred to the primary, that is using this equation. That is, your impedance ZL on the secondary side of the transformer, when it is referred to the primary side of the transformer, it will become A square times of ZL. Whereas value of A is nothing but the turns ratio of the transformer written as N1 divided by N2. So, if you want to look at an example on this particular problem, we have this particular transformer representation where the impedance on the secondary side can be represented on the primary or referred to primary by converting that impedance using the turns ratio. Now, have a look at this particular example where you have a load resistance and the value of the load resistance is 20 ohm. Now, we wanted to have an equivalent representation of this particular equivalent circuit by moving this resistance onto the primary side of the transformer using the turns ratio. Now, if we consider that the turns ratio A is N1 upon N2, then when this resistance is moved on to the primary side, you can say that resistance is going to be A square times of RL. And now, if we transform that resistance to refer to primary, then we can neglect this particular transformer and represent it like a simple circuit. That's what we are doing here, where your resistance is moved onto the primary side of the transformer and you don't have a transformer, and your series resistance, which is already on the primary side, remains same, but whatever the resistance brought from the secondary side referred to the primary will be A square times of RL. Then if you wanted to calculate current that is flowing from the voltage source V1, the expression for I1 is going to be V1 upon RL or RT plus A square times of RL for us. That's where we'll be able to calculate the amount of that is current coming from the primary side of the transformer.